we are going to take two talks in one. It's basically the same subject, and it's about integrating renewable resources on the grid. And first, we'll have the first part by Professor Friedrich Wagner from the Max Planck Institute for Plasma Physics. And then we'll have Hubert Flocard from CNRS. So first, Friedrich.
Okay, thank you very much. Good afternoon. Thanks to the organizers for inviting me. I'm here the second time, it's great. The last time was summer, this time it's winter, with very nice, spectacular views, in case you have time to look out. The topic is properties of an electricity system, so I will only talk about electricity, nothing else. And my story goes around the Energiewende of Germany. What you see in blue is the development of the installed onshore wind power in Germany from 1996 to now, 2013. And on the right side, you see the same diagram now for photovoltaic.
That's peak power.
This is installed power. So this is an exponential function. It's not exponential growth, but the photovoltaic is represented by an exponential variation in time. So it is a tremendous increase. Just to remind you, this is the load curve on Germany. It shows on winter, of course, we need more than in summer, and then it has the fluctuations, which are the weekly fluctuations and the daily fluctuations. Just to remind you, when you look into a month, the month of January 2010 in this case, or then summer, July, then you have the variation, the daily variation, Monday through Friday, at large load values, and then, of course, interrupted during the night with low values, and then you have Saturday, Sunday, and this repeats itself continuously. The winter level is higher than the summer level. And then down you can see in blue wind. Wind is, of course, stronger in winter than it is in summer. And here you have photovoltaic, which is more prominent in summer than, of course, than, as you can see here, in winter.
Excuse me. That means that the consumption is the same in winter and in summer? The black curve?
No, this is what I said. This is January, this is December. So in winter we have, from the tendency point of view, more. In winter and summer we have less. When you look at the peak value, the same when you look at the base value. So this is the peak value in winter, and this is the peak value in summer, the base value in summer. Sorry, this is the peak value in winter, and you can see that in summer it is less, and this is the situation here in winter, and it is also less. So it's something, the difference is something like maybe 8 or 10 gigawatt.
That's the demand.
This is, yes.
The black curve is the demand.
Yeah. Now when I use this curve and I plot into this the present situation with onshore wind and photovoltaic, then you can see that the sum already goes deeply into the demand curve, which means then, so it is in total here 32 gigawatts onshore wind, not very much offshore wind, and then photovoltaic power, which again is very large, larger than wind. And we have now a situation that the renewable energies have feed-in priority, so what is produced goes into the grid, and already now we have periods without thermal power, because this is larger than, for example, the lowest values there, and we have periods with surplus, because this is larger than the lowest value here. So this is the present day situation in Germany. Now this is not expected. This shows sort of the expected development from 2009, our Ministry of Environment, and here you can see how they expected that onshore wind will develop and how they expected how photovoltaic will develop, 2010, 2015, so we are somewhere in here. And what actually has happened is this situation. So with winds, they were not so bad, but with photovoltaic, they were very lousy in their prediction. So the actual development driven by the feed-in tariff system was much, much stronger than anticipated. So the consequences of this rapid development, high costs. Last year we paid 22 billion euros feed-in tariff for an electricity which had a market value of about 2 billion euros. We have a totally unbalanced development because we are developing sources but not new grids. And we do not have technical solutions for several components, for example, storage. Now the electricity production from 2010 to 2013 is shown here and how it splits up between coal, lignites, and so on and so on. I walk you a little bit through the table, don't read everything now. Here the percent applies only to the 2013 year. When we look into the mix, photovoltaic and wind, these are the scalable forms because hydro and waste is all limited. So the scalable ones now have 12.4%. The renewable in total are 23.4% because we have quite a distinct contribution from biomass, 42.6 terawatt hours. I should have said this, so these are terawatt hours, 6.8%. Then this is the remaining nuclear part, and this is the fossil part. So dominating still, of course, is fossil. Here you can see the strong growth in energy, so in terawatt hours of the renewables. So this is the development of wind. Of course, it changes from year to year somewhat, and this is the rapid development of photovoltaic power. Here you can see the planned decrease of nuclear energy. It was once 141, now it is 97 terawatt hours. This is the increase of coal use. So this is coal, this is lignite, specifically lignites. There's a strong increase in this part. And then there is a strong decrease in gas from 89 to 66, so nearly 30% less. So the reaction of the economy in this period is that gas now is too expensive in spite of the beneficial properties it has with respect to operating turbines. Gas power stations are mothballed now, not operated any longer. And this is a legality issue now, how to continue with those because we need them. Cheap coal replaces gas in spite of the higher specific CO2 production of coal, which is nearly lignite twice the one of gas. And the environmental consequences are that in Germany, despite the fact that we deploy a lot of renewable energies, CO2 increases. 2011 we had 798 million tons, and now we have 834, an increase of 4.5%. So what I did is very, very simple. I have to apologize for this. I take data which we have available in Germany for wind, photovoltaic load and so on, or demand, and then I just scale them to higher values. I did this for 2010, and I show you now the results for 2012. The data, of course, are better. We have more power on one side, but we also now have offshore wind power. And I do not have to calculate offshore wind from the velocity, the wind speed. I can directly use data and scale them. So this is much simpler and not very sophisticated in comparison to what has been presented to you in the last 2 days. So I take the data 2012, the 4 suppliers which we have in Germany. I have then ultimately a database for the load on offshore wind photovoltaic. My resolution is 15 minutes, and I have then for each of this quantity 35,000 something time points. The procedure is scale them up and analyze them. The assumptions are the electricity demand will not change. I would expect, let me say, that saving primary energy would need electricity. Then we, of course, all know that we are discussing electric cars, so that the improvement in overall efficiency is compensated by further expansion of electricity in different areas like mobility. I also assume that hydro and waste does not change. For sure, waste should not increase. We should save waste. And I just subtract these contributions from the loads, and then I come to the reduced load, which I take 500 terawatt hours for Germany. So the total electricity production is something like 620 or so terawatt hours. The net electricity production is something like 580 terawatt hours. When I subtract now hydro, waste, and so on, I come to a target of around 500 terawatt hours. This is what I want to do. I do not include biomass because this will be used for transportation. I also think, like you, that this is mostly aviation because there is no other possibility. And I do not assume that this is used for electricity production. In case it is used for electricity production, about 10% of the demand could maximally be covered in Germany by biogas. Maximally Here, this contains what I before mentioned in another context, what the biologists tell us. I don't assume losses. This is, for a physicist, not interesting. No nuclear, nothing imported, which of course will not be the reality, I'm sure of this. And then I assume that the wind shear between onshore and offshore is 2/3 here, 1/3 here, but this mix is rather uncritical. Okay, so these are my input data. Again, the reduced load here, this is the PV situation with more in summer. This is onshore and offshore wind. This is just a guide to the line so that you can see, of course, in summer it's more. Here in winter it is more. This represents the turbulent nature of the wind. This is different in offshore wind because here the turbine has to follow its specific characteristic, power against velocity, and it operates in a larger range between 13.5 and 30 meters per second at constant power. Therefore, you have sort of a totally different situation here in the characteristic because it is limited, unlike the onshore wind case. This is multiplied by a factor of 200 because at the moment, as I've shown to you, we have little, and simply to have it at the same ordinate, I multiplied it here. Offshore wind here for 2012 was 160 megawatts, which I could use. Okay, this is the installed power in each of the cases. I have, of course, corrected for these calculations the growth during the year, specifically photovoltaic, changed quite drastically during the year. So this is corrected in the sense that ultimately I use the installed power at the end, and at the beginning this is all normalized to this high value. So that I can now, so that I have a constant installed power for all three supply sources, which I then can scale to higher powers. Okay, so the installed power is given here as a line, so there is a utilization factor, something like this. In these three cases, here I assume 100%, I don't know anything else. And this helps me to calculate from my database data into the actually installed power, which is ultimately necessary to produce this distribution. Okay, the duration curve now, this is the reduced load, the way I defined it. This is the residual load, the backup power. This here, yellow is photovoltaic power. This is onshore wind, and this is the scaled up offshore wind. And here again, you can see the different characteristics here because of this plateau character of offshore wind. This is the nuclear part in Germany at the moment. This is the fossil part, which produces CO2. And you can also see, for example, that photovoltaic power, of course, only contributes half a year. The rest is night. And you can also see that we can only enjoy from the installed onshore wind power more than 50% of the available power for only a month. Then it already falls below the peak installed value here. So it's only a short period where you have more than 50% of the installed power. Okay, so what I do, my exercise is now I scale it up and I show it to you on the onshore data there. Exclusively onshore at the moment, no mix. So this is the power, and this is the time. This is again the demand curve, and this is now the onshore wind contribution when I assume 25%, 50%, 100%. The 100% case is for me the specific case. This is the equal energy case in the sense that in the renewable energy, in this case only onshore wind, to demonstrate what I want to do, produces as much energy as integrally we need in our case here. You can already see that for the 100% case, we are now in a different ordinate here. This is a factor of 3 higher than what I have shown you before. So we need, as a consequence, large capacitors, of course, to produce energy in these cases. So when we now only concentrate on the equal energy case, the 100% case, then we produce surplus, which is in yellow, everything which is above the demand. And we still, under these circumstances, of course, we have a need because here we don't meet the demand curve. So this integral is something which has to become from the outside, at the moment from a backup system. And if we had storage, then this would be plugged into here, and then we would be CO2 free. And this is the situation why I stopped in my computations at 100%. Okay, so this is the 100% equal energy case. This is a very specific case, but you understand what I mean with it. Okay, we saw that photovoltaic has another average variation during the year than wind, for example. And photovoltaic, for example, is high in summer, wind is high in winter. And on the other side, we also know that wind is very erratic, whereas photovoltaic is periodic, and photovoltaic contributions is during the day where the load is large. So these factors ultimately allow us to combine photovoltaic and wind in an optimal fashion. And this is shown here. I minimize the backup energy needed because this produces CO2. I plot it here against the photovoltaic energy, and each of them are normalized to the reduced loads. And here I have then various curves, and here the parameter is now the total renewable energy, again normalized to the reduced load. So you can see that indeed there is a minimum. So I need, let me say, a certain fraction of photovoltaic energy to minimize this quantity. This minimum is very flat. So it is not very crucial. But it makes a difference, let me say, when I operate here for the 100% case without any photovoltaic or without any wind power. It makes a difference here, a distinct difference. Now the red line here, the 100% case is for 2010. Then the squares here are for 2012, and you can see it is basically the same. The weather pattern doesn't matter very much. And the dots, the green symbols are the onshore wind only, and this the offshore wind only, and the curves are also the same, and this shows that it is not very crucial how I mix onshore wind and offshore wind. And ultimately, I have here a minimum, and this would be is for me the 100% energy case under optimal mix conditions. And the optimal mix here is not a development scenario. Those who are building windmills and those who are putting solar panels on their roofs, these are totally different market participants. So this is not what I mean ultimately will happen, but for me it is a reference case so that it is well defined, and it is the reference case of minimal side effects. So every other case would have more consequences, and what the consequences are, I'll let you know. Okay, so when we now scale, I show here against the installed renewable energy power, the annually produced energy, the directly used renewable energy, the one which is, I'm done, 20 minutes? 10 minutes. I have 10 minutes, okay. The directly used renewable energy, the surplus energy, and the backup energy. So these curves are linear, which of course does not reflect the reality, because when we increase it now to the 100% case, which is the 500 terawatt hours, then of course more and more one has to integrate not so favorable sites for wind energy. At the moment we are using the best, and so on and so on. So these curves will also be bent, but this is not my story here. Okay, so this is the equal energy case where I stop. And here I have exclusively offshore wind, here I have onshore wind, here I have photovoltaic, and here I have the optimal mix case. So what we can deduce, for example, now here is the full load hours of these systems, because it is energy against installed power. And onshore wind for 2012 is out of these 8,760 plus 96, because it was a leap year. 1,547 hours. Offshore is nearly 50%. Photovoltaic is only something like 10% or a little bit more. Or here we see it in the capacity factor, which is the full load hours against now the number of hours, 8,784. 80% for onshore wind, 47% for offshore wind, 11% for photovoltaic. We see that the directly used renewable energy part saturates. It saturates, of course, in periods where we don't have wind or sun, and of course the saturation is very strong in case of photovoltaic power, because in the night you don't have anything. So it is just not possible to go up to 500 terawatt hours. The surplus comes very strongly and from a certain level on, and of course here we see that the backup energy, which is either storage or at the moment fossil power, thermal power, this is strongly reduced, and this is the idea behind all these exercises. Okay, we can see that photovoltaic needs the highest installed power, The directly used part of the energy is lowest. It produces the largest surplus, and it has the least effect on the backup energy. And this is a specific feature of this supply form. When we now look where we are in Germany, here we are. Onshore wind, photovoltaic, offshore wind. And this is where, under the optimal mix condition, we have to go in case of the 100% supply situation. Here we have to go to offshore wind. Onshore wind, this is this 1/3, 2/3, and this is the photovoltaic contribution fixed according to the minimum effort level, the optimal situation. So the experience already now where we are here, because we still have to go quite a while, the experience now is the technology change has to happen outside market rules. High costs for the consumers, insufficient grids, destruction of our photovoltaic industry, despite the fact that a lot of effort went into this. Economic problems of the wind industry at present, and a strong transformation of landscape. I know what I'm talking about because I'm living in the north, where all the windmills are. And if you had something like this, I wonder what Claude Monet would have done in his impressionistic phase. Okay, so when I now look into the specification of the 100% optimal mix case, you know my assumptions. So the specification would be that onshore wind produces this amount of terawatt hours, offshore wind this amount, photovoltaic this amount. The backup is still needed. You remember this one area which is not filled, 131 terawatt hours, and because it is the equal energy case, this corresponds to the backup. And if we, to the surplus. And if we had a storage, then these things would be compensated and things would be fine. And this is the installed power for onshore, offshore wind, photovoltaic. The sum of those is 306 gigawatt. The installed power compares nearly with the load, with the minimal load of Europe. So with this sort of installed power, when everything is optimal, wind and photovoltaic, we can then basically feed Europe. And this is still the contribution of the loads. So this is the load and this is the backup. So as it was also shown yesterday already in Professor Erdmann's talk, we still need a lot of backup capacity. We can reduce it somewhat, 12%, something like this, but not more. Okay, now because of time, let me just say what else one can study under these circumstances. I can study the challenges on the backup system. What is the dynamics of the backup system in the future when its dynamic is not determined by the load variation, rather by, let me say, the strong variability of the wind. This is delta P over P, jumps within 15 minutes. This is my time resolution. And this is the load situation. So this is something our system absorbs. And now you can see what happens when we have onshore wind, offshore wind, or photovoltaic. You can see that these excursions, both positive and negative, strongly change. The optimum mix is, of course, more favorable than all the others. Then you can look at the same thing into the grid. Whereas the dynamics of the backup system is only determined in the level between 0 and the load, now it is determined between 0 and the installed capacity. So the dynamics for the grid is much, much larger. And you can see here again the red circle, in case you can see it. The red circle is the previous situation. And this is now the situation with onshore wind alone, offshore wind alone, or then the optimal mix case. So the optimal mix case, of course, is beneficial. But nevertheless, the dynamics is tremendous. And the system have to cope with this, of course. This shows now, previously I showed you the amplitude, now I show you the frequency, how often does it happen. And this is simply sort of an histogram. Here I have the jumps in delta P as defined before. And this is the line which we have following simply the excursions of the load. When we now go to the optimal mix case, this one, then we get the crosses here. And you can see that there is a strong development in the dynamics. So power jumps between 4 and 5 gigawatt now, which were here 10 times in a year. We have now 1,000 times in a year. And you can also see here that when we go, when we compare, let me say, we have a certain number of large power changes here, which at the end require some sort of coherent action of the residual system which we have. So we need, let me say, then something like 10 gigawatts or so, which have to work in a coherent fashion to outbalance the jumps from the intermittency introduced by wind and photovoltaic. Storage, in Germany, the situation is that we have 50 gigawatt hours and 7 gigawatts. For the 100% optimal mix case, we need 33 terawatt hours, a factor of 650 more. So this is impossible. Just to play around with figures, I satisfied myself with 5 terawatt hours. This would be a system which would be described when I incorporate 5 terawatt hours. So the backup system is still necessary at the level of 71, and it produces 42 terawatt hours in this case. The economy of the whole system, of each of the components, is determined by the capacity factor. So this is the capacity factor of onshore wind, which I have shown you. This is the higher one, 47, for offshore photovoltaic, storage system, backup system. So none of these systems is operated economically. I don't know exactly where the economic limit is, but there are so many economists, maybe somebody tells me. So, but for sure, one situation is that the structure of the electricity cost is alpha divided by the capacity factor plus OC, and alpha represents the capital costs and this the operational costs. So if you have a system which has no operational costs, it depends very sensitively on this quantity. So this is a crucial economic element. Another interesting thing is when I analyze the spot market, 1 minute. Okay, then I skip this and I go to my summary. Well, let me just say one thing. Because of the demand side elements, when I look into the demand side issues, is it here? No, it is here. Then even under, well, the demand side means I avoid high cost periods and I shift my economic activities into low cost periods. Nevertheless, when I do this, as our life is periodic, because the sun cycle is periodic, also these activities will require a certain periodicity. It will not be possible, I think, that the grid operator says, meteorology tells us that tomorrow we will have a lot of sun, and then every boss calls his collaborators and say, okay, tomorrow we will start working. So there will also then be a certain periodicity. And this is what I would like to analyze. And this means I can average over the whole week, over the whole year, and now represent a day in its demands and what in the average the surplus is doing and the backup is doing. And this is this average outcome which says from 9:30 to 5:30 now the surplus is above the backup. And this now would be the low cost periods because surplus is here. So this shows us, because of photovoltaic, the favorable situation, cost situation is not during the night, it is during the day. So this fact will drive to increase the economic activities even further during the day. So it will intensify the day. Of course, there are certain fringing elements here, and for sure economy, let me say, will find ways to utilize those. But the basic message is we have to intensify our activities when they are already high. So you can now look into the winter separately and into the summer separately, and then you can see, let me say, you have sort of an oscillatory behavior, and I wonder how industry now will cope with this phasing or so. I don't think they will be able to do this. And of course, in summer, circumstances are worse. Here we have the window where electricity is cheap. And the only effect is now when I look into the weekend. In the weekend, I have tremendous surplus and I don't need any backup any longer. So weekend is very cheap. So the biggest effect is now integrate the weekends. So when we do this and we additionally use the renewable energies, then we can use 7.5 terawatt hours. The peak load is reduced to 71 megawatt. The backup system is also reduced. So demand side management will drive us and change our Christian traditions to operate things also during the weekends. And one final thing, then I'm done. Going to renewable energies in a situation like Germany, where we have a lot of fossil fuels, of course, reduces CO2. And this is the reduction of the specific CO2, so the kilogram CO2 per kilowatt hour. This decreases like this when I just stay with the present fossil mix. This is the variation when I change everything into gas. When I now add storage, then you can see I can improve those things with my storage. This would be the 33 terawatt hour storage, then everything is out, no CO2 any longer. This is the 5 terawatt hour, and this is the reason why I picked 5 terawatt hour, because the major part is done with 5 terawatt hour. But irrespective of this, the big effect is here, and then there is a little additional effect. So I would conclude that storage will not be motivated by additional CO2 saving. It will be too expensive at the too little effect it produces. And when we now look into the German situation, we are here at the moment. We are not here because we still have nuclear. This is only fossil fuel at the present mix. So this is the situation of Germany. This is the situation of France, of Switzerland, of Sweden, and of Norway. And you can see how tremendously the effort has to be with renewable energies plus storage to get to the low levels which are already available in Europe, here in your country and in other countries. And you are already here where others would like to be 2050. Denmark is up here. This is very astonishing because they have something like nearly 30% of wind energy. But when you look into, well, maybe I don't discuss this. But this is simply when you use coal to compensate wind. Okay, I'm done. Conclusions, large powers are necessary. A supply system exclusively with wind and photovoltaic does not seem to be possible. Backup systems is required in all scenarios. Little savings, 12% or so in thermal power. Power heat coupling, maybe in winter, in the mornings and evenings. Probably not very attractive. See the experience of Denmark. This was already mentioned. High surplus power peaks, what to do with. At the moment, we send them to the Czech Republic. To further suppress it, this degrades the economic operation of the renewable systems. Use for power to gas, high prices of the secondary electricity. Use for heating, winter production, yes, we could utilize 76 terawatt hours out of 550 necessary, something like 15%. Use for cooling in summer, this would be fine. We have 55 terawatt surplus available, and we would only need for cooling 20 terawatt hours. I skipped this. So finally, the exclusive use of renewable energies has limitations and leads to shortcomings. Therefore, the most obvious question will be whether and how an electricity system based on variable sources can be improved and supplemented. This will be a question classically posed to research and engineering, because these disciplines have found the ways in the past to liberate mankind from the imponderabilities and perils of nature. Thank you.